talk. Can you hear me?
Yes, yes.
Oh, perfect. So again, I'm super excited to introduce Payam because she is also one of my colleagues at ITU University, and I think her research is super exciting. So Payam, are you going to need to share your screen? Do you have
yes, yeah.
And you have the ability to do that?
Yes, it looks like, yeah.
Okay, perfect. I'll hand it over to you then.
Okay, thank you. So do you see my slide?
Yes, perfect.
Okay, perfect. Hello, good morning or good evening, depending on where you are. My name is Payam Zahadat from the ITU University of Copenhagen, and I have the pleasure today to present this work to you, Incentive for Self-Protection in a Collective System, a Swarm Robotics case study. So the work is about swarm robotics, and I will talk about evolutionary swarm robotics and indirect evolution for controller design in a robotic swarm. And in this case, about incentive-based evolution for self-protection. So when we try to develop controllers for robots, we can take a manual approach, or we can design based on some rules, or we can take evolutionary approach. So in the previous talks, there was quite some information about evolutionary robotics, and this work is also in that context. Sometimes we have a single robot to design a controller for, but sometimes there is a group of robots that are supposed to do something together. So the switch from, in the controller design, the switch from a single robot to a group of robots is not trivial. The reason is that there is no linear relation between the behavior of a single robot and a group of robots. We have more considerations that we need to make, for example, communication and interaction between the robots and their coordination, for example, or possible physical interferences and so on. So the task is more complex in this case. When we talk about swarm robotics, in most cases, we mean several robots, usually similar robots, which are relatively simple and weak. And they are usually relatively noisy in the behavior that they can do, and rely mainly on local interactions and local sampling of environment, local sensing. The idea is that these simple and weak robots, which cannot do something interesting or that much in as individuals, they can do some, they can achieve something useful as a group. So here you see some images from nature. There are very interesting examples of swarm intelligence and swarm behaviors in nature. And of course, it would be very natural for us to take at least some inspiration from nature when we try to design controllers for artificial swarms. So this work is in the context of evolutionary swarm robotics. We can have direct or indirect approach towards designing controllers here. In the traditional evolution, we have the direct approach. So we directly target a given task. We define a fitness function that evaluates how good the swarm is acting to perform the task. And so that's very direct. The problem here is that because we need to design the fitness, and there are sometimes we can get stuck in local minima because there might be some stepping stones toward the solution, which is a complex solution, and we don't know how these stepping stones look like. So we don't know how to design the fitness to help the evolution to get to the desired target. There are other approaches. For example, embodied evolution in the context of swarm robotics, evolutionary swarm robotics, that's a relatively indirect approach. So here we have the evolutionary population distributed over a population of robots, and there is the interaction between the robots, and the survival of the controllers is based on these interactions. So we can also include aspects of target task in the survival. So we can combine aspects of environment, interaction, and task. So it's an ecosystem-based and more artificial life-like method. We also have novelty search, which is not specific to swarm robotics, but in general. And in novelty search, we target diversity of behaviors. We try to take some inspiration from nature, and the way things work in nature is a little bit different than the traditional way. So we don't have any specific task to target. The way it happens is that some organisms live and interact with each other, and some of them survive, and then afterward, at some stage, we look at the survived organisms, and we know that the behaviors that they show contain some solutions for the environment that they were in. So here I would like to talk to you about another approach which uses a similar thinking. So this approach is called incentive-based evolution for developing swarm behaviors. We evolve controllers to get our robots to behave according to an individual principle or individual incentive. The idea is that in nature, there seem to be some repetitive patterns of individual principles or forces or incentives, and some collective behaviors are emerged as their side effects. So like a natural consequence of these individual incentives. So we evolve individual controllers to our certain principles, and afterwards we look at the resulted collective behaviors and pick the interesting ones, and we can also tune the parameters. There are some studies about incentive-based controller design. One is takes the incentive of maximization of future options. So here the agents seek to increase the number of potential states that they might encounter in the future to hopefully increase the evolutionary fitness for survival by keeping more options open for the future. I will be back to that in a minute. Another incentive that has been studied is active maximization of predictability. So the idea is based on minimization of free energy suggested by Carl Friston in this context. And here we try to actively maximize predictability of the perceived environment with the hope to have a better survival by predicting the future disturbances in the environment on time, and we can react on time. So let's have another look at the maximization of future options. Here our robot wants just to be in a position with more opportunities in the future. And from the perspective of our robot, it sees itself as this red dot and sees the other robot as this blue dot. And it thinks that the other robot will go forward all the time, for example. And our robot has 5 actions it can make. It can be in these 5 positions in the next step. So for example, if it takes the turning left action, it will have other options in the future. And here we see in the 5 steps in future what positions it can, what possibilities it has. In some of these positions, there will be some clash with the other robot. So what our robot does is that it counts the number of future possibilities which are safe, so there is no clash. And it counts it for all these 5 actions, and it picks the action which gives it the maximum possibility in the future. This has been used in some simulation studies, and a very nice result has emerged, which is collective motion, very similar to flocking in real natural flocking. We also have as I mentioned before, we have the incentive for active maximization of predictability. And here we try to actively maximize predictability of the future. That means the robot can learn to predict the future better, but it can also take actions that positions it in a better place. So, for example, moves to a more predictable region, or change even the local environment to make it less fluctuating and more predictable. So that's the main idea. So here our robot just wants to be in a place where things are predictable. And we can implement this idea, for example, by having a neural network which takes current state of the board and the action of the robot and predicts the future and suggests the next action for the robot. That has been also studied and led to certain order formations. For example, here the agents are they are aggregating in some place, and here we have some line formations, or we can have dispersion and so on. So it seems that the agents want to be in safe position. So that would be an interpretation of this behavior and a different level of abstraction of a possible principle. So if they want to be in a safe place, why not the robot tries to follow an incentive for self-protection? So just try to be protected. This will be the contribution of this work here. So when I was thinking about this, I had an eye on the behaviors like what we have in penguin huddling, for example. So in the emperor penguins, they want to avoid wind and cold. So you just to get a little bit of impression what happens in the penguins, they take turns to be inside or outside, like at the borders of the group. So the ones who are inside, they will stay warmer, and the ones in the outside will get colder. But because they take turns, all of them will be in a more or less good situation. So the main idea would be to the incentive for being inside once in a while with some tolerance for being outside. So being inside once in a given period of time. So that's what I try to implement here. So the robot controller here is an artificial neural network and is identical for all the robots. And the different robots might get different inputs from the sensors, and they can act differently. So the actions that they can have is that they can still stand still, or they can move forward fast, turn left, or turn right. About the sensors, every robot has 8 sensors with 2 thresholds. So if there is nothing detected in these thresholds, the sensor returns a 0. If there is something detected in this region, it returns 1. And if it's very close, it returns a 2, meaning that there is somebody close. The artificial neural network is feed forward, and it gets previous and current sensor state, and also previous step size and the rotation of the action. And the output is one of the 5 actions that the robot can take. There is relocation noise, meaning that if there is a motion, it will not be perfect. So there will be some noise. We have a toroidal arena with some dimensions, and we have 50 robots in the arena. So the way that the self-protection is defined is that the self-protection level of every robot is defined as the maximum number of occupied sensors in a window of tolerance. So in tau steps, 50 time steps, we look back and count the number of occupied sensors, so how protected the robot feels, and we pick the maximum. So there is some tolerance. We pick always the best of these time steps. The fitness function for later evolution is the average of these protection levels over the whole swap. So I evolved a population of 50 neural networks for 200 generations. And there is some progress in the fitness. And this is one example behavior that you can see. So the lines here, they show that the robots can see each other. So there is some interaction. And as you can see, there are some small aggregates that are forming. And over time, some of these aggregates are dissolved into the larger aggregates. In this example, we will end up with one large aggregate. And an interesting point about this aggregation behavior is that it is dynamic. So we have these motions, they change position. So to have a look at an example robot, we have the trace of a robot in relation to others in an example aggregate. So this black line shows the trace of the focal robot, and the blue lines show the traces of the other robots. So the robot starts here at some point, and it moves around, and it will be at the border at some time, then it will be again inside, and then again outside. So there is some going inside and outside, a little bit similar to the penguins. Not exactly, of course, but it has some similarities. So what we did here is that we took an indirect approach. We didn't target aggregation or anything. So we evolved for an incentive for self-protection. And it leads to aggregation, some dynamic aggregation. So why not targeting aggregation now? So we now take the direct approach and target aggregation, and we want to see how they compare. So for evolving directly for aggregation, the fitness function is defined as the largest cluster size scaled by the swarm size. And again, with 50 neural networks evolved for 200 generations, we have some progress in the fitness. And this is an example behavior here. So here again, we see the formation of small aggregates, and the aggregates can be even just two robots staying around for some time, but then they dissolve, and they all form one large aggregate. So just if you would like to have a look at both behaviors at the same time, here we see that in the when we evolved directly for the aggregation, we have more static aggregate, and when we evolved for the self-protection incentive, the behavior is dynamic. In both cases, in these examples, we have one large aggregate at the end, but that's not the case all the time. So here we can have a look at the behaviors resulted from the different methods that we just saw. And we looked at the state of the swarm after 5,000 time steps. So at the x-axis, we see the largest aggregate size, and at the y-axis, we see the number of aggregates. So at least two robots seeing each other. And we have the results from 10 runs with the best controllers from aggregation and from incentive, and also 10 random controllers. We see here that in the aggregation experiment, after 5,000 steps, we often end up to one large aggregate consisting of most of the robots in the swarm. And in the incentive-based experiment, after 5,000 steps, we usually have 2 or 3 aggregates. One of these aggregates at least consists of about half of the swarm members. And with the random controllers, we do not have any real aggregates. Here we can have a look at the average motion of the behaviors from these two experiments. And as we saw before, in the incentive experiment, we have a lot of motions. And in the aggregation experiment, we don't have much motions in most of the cases. But what is the reason for these motions? Why the aggregates are dynamic when we have the incentive-based? So here you see a snapshot, And these blue lines, these curly lines, they show that the the robots were moving around. So it shows the motion. So let's have another look at the fitness function, how we defined it. The fitness is defined as the average of the protection level, and the protection level is defined as the maximum protection or occupied sensors in a window of tolerance. Maybe this window of tolerance that is encoded in the incentive and allows for some agents to be inside and then leave their place to let others to be inside. So that maybe is the reason for this dynamic. So I wanted to have a look at that and a very quick look at that. So I evolved for self-protection, but this time without the window of tolerance. So the window was 1. And with evolving some populations for this case, we end up, here you see one example. So we end up again to some aggregates, but the aggregates are not dynamic. We don't see those curly lines of traces here. So the aggregates are not dynamic. So yes, maybe that is the reason. Maybe the window of tolerance is the reason for this dynamicity. So I also had a look at the scalability. So how the evolved behaviors scale with the swarm size. We test the best evolved controllers with 50 robots in the swarm. I picked the best one and used it in a larger and in a smaller swarm. So here we can see the result. The y-axis shows the relative aggregate size, which is the largest cluster size divided by the swarm size. That's actually the fitness that we used for the direct aggregation. The box plots in the middle, the orange ones, show the results from 50 robots. So that's what we evolved for. And as we also saw before, when we have the aggregation experiment, we had quite a large relative aggregate size, because it, in many cases, we end up with one large aggregate. And in the incentive experiment, at the same time, we end up with 2 or 3 aggregates. So the relative aggregate size is smaller. If you look at the case with 100 robots, we see a drop in the performance. So both behave more or less the same. But if we look at the experiment with 20 robots, we have a drop off in the performance for the aggregation experiment, which is quite a lot, but raise in the performance for the incentive-based experiment. So it looks like when we evolve directly for the aggregation, the resulted behavior needs a high density. So it is more sensitive to the swarm density, but that's not the case in the incentive base. It looks like more or less the same size of the aggregates are formed also with this smaller size of swarm. So to wrap up, here we used the identical controllers with the individual fitness average over the whole swarm for the incentive base. And that actually looks like something very well suited for being used by distributed evolution. So for example, embodied evolution can fit well here. So that would be something to look at. One interesting point was that dynamicity of behavior and this window of tolerance seem to be related. So that's also something that seems interesting to look at maybe more closer here, but also in other contexts. And a general question that we have is that what kind of behaviors are achievable indirectly? So yes, approaching controller development indirectly seems to give us more options, more in a more explorative way. because when we do not directly target specific collective behaviors, we may reach interesting or unexpected behaviors. And that seems nice. But what kind of behaviors we can expect, and what kind of incentives we should try, and how we should encode or implement such incentives. So these are all open questions that we can think about it. So thank you very much for listening, and if there is some questions, I will be happy.
Thanks, Payam. That was a really good talk, and how can anyone not like a talk with really cute penguins then? So I see that Professor Stoy has a question. So you can unmute yourself, Casper, and ask away.
Hello, Payam. Thank you for the talk. Very inspiring. I was just wondering, have you thought about what happens if you introduce obstacles? Because I mean, I guess it's a going along the idea of more complex behaviors. Do you know what will happen if there are obstacles in the environment? Would they cluster around those or avoid them? Or
I didn't try it, but I thought about it. I thought maybe I would expect that they like aggregate around that, so they use it as a place to be safe. And yeah, I also thought, even if they can move around some obstacles, maybe we can end up to some formation, so they build something in a longer try. Yeah, but that's something that I would like to look at.
Thank you.
Any more questions, or I will steal a question from Payam? Okay. So one thing that I was thinking while you were talking was, is it beneficial for the swarm for all the members to be in a single aggregate? Like, you could imagine if, well, for example, if they're all in one cluster and then a robot eating monster came and attacked that one cluster, then that kind of destroys most of the population. Would it be more advantageous for them to cluster in like 2 or 3 groups? Do you have any thoughts on that?
Yeah, you mean like in a longer evolutionary perspective? Probably, yeah, but that's also interesting. Yeah, I would say, I mean, I can imagine that it is, yeah, it is more, maybe more, but it also depends on the behavior of the, like the capabilities of the robots. So if and also the how bad is the attack, or how powerful is the attacker. So if it just like scratch the surface of the group, or if it really harms the whole group. So maybe different strategies would be useful in the different cases, like depending on how strong is the attacker.
Perfect. And then Hyan has a question also. So feel free to unmute and go ahead.
Yep. Thank you for the talk. I was just wondering about the results that you had when you were evolving the controllers directly. So when you had them going straight for aggregation. Do you know why, when you had the increase in the agent density, or increase in the number of robots within your simulations, why did the performance decrease? Do you know why that would be the case?
Swarm?
Yep.
Yeah. So I'm guessing that this aggregation, because we target the aggregation with 50 robots, for example. So maybe the behavior, the behavior of the single robots, it's more specific, more like tailored for this number. So when we have a larger swarm, maybe they cannot really cope up. So because there will be some interferences, and they can like block each other's. So that would be my guess, actually.
Okay, totally understand. Thank you.
Okay, I think that's working out really nicely for time, actually. And I like that Hian asked the last question because he is now ready to talk.